Welcome, boys and girls, to another video. Yes, sir. Welcome to another video. Today we'll be busy with chemistry. You know what I'm saying? Chemistry today, people. So today we'll be looking at redox reactions. Okay, redox reaction, a very important topic here. Okay, so what is a redox reaction? Well, a reaction in which electrons are transferred, right? So here I got two atoms, people. Atom A and atom B. So as it seems here, atom A is giving this electron to atom B. So this scenario here where atom A is giving atom B an electron is called a redox reaction. A reaction in which electrons are transferred because this electron here is being transferred to B right there. Now, what do we call this when this electron is given to B? So B is receiving the electron, B is given the electron, so B is gaining an electron. So B is undergoing reduction. Reduction is a gain of electrons. Then we have A. So since A is giving away that electron, then what is happening to A? Because something has to give here, something has to happen to A. So A is losing an electron, which means A is undergoing oxidation. Oxidation, which is a loss of electrons. Oil for oxidation is loss, right? Then rig for reduction. Reduction is gain. Okay, so use those ones. Don't underestimate these acronyms here. I'm telling you, if you use this, you're gonna remember. If you have a hard time with your memory, trust me, this is the one for you. This is the acronym for you. This here is for you. Now moving on to the example. Okay, so I have the following example. Okay, this is a redox reaction. The reason why I'm saying this is a redox reaction is because there's a change in the oxidation number, which I'll explain later. So as you can see here, these are individual atoms. They are not ions yet. Okay, they're not ions at all. They're neutral atoms, electrically neutral atoms on their own. So they have an oxidation number of 0 and a charge of 0. In fact, let's not speak of charge. You have an oxidation number of 0. Know that because they're electrically neutral atoms on their own. So when they get over to the product side, what happens to them? Well, now they gain. Now the oxidation numbers increase and decrease. Okay, so here's what I'm trying to explain here in this example. When the oxidation number increases, that means that certain substance is undergoing oxidation. So as you can see, it increased from 0 to +1. So Na is oxidized, and this one decreased from 0 to -1. 0 to -1, that Cl is reduced. Na is +1 because it's in group 1, and Cl it's -1 because it's in group Cl is -1 because it's in group 7. It's a halogen, people. I'll explain that one too later. Just make sure you're hearing me and make sure we're on the same page here, because everything that I'm saying right now, it'll all make sense once I explain everything that's going on with redox reactions. Moving on to oxidizing and reducing agents. Now, we have these agents called oxidizing agent and reducing agent when we're talking about redox reactions. Now, what is this oxidizing agent and reducing agent? Well, let me explain that for you. An oxidizing agent makes oxidation happen. You're probably wondering, what makes oxidation happen, buddy? You speaking a lot of baloney here. Listen, remember we talked about oxidation. So when I'm saying an oxidation agent or an oxidizing agent makes oxidation happen, I mean, yes, that agent causes something to be oxidized, which means it makes something lose electrons. Correct. Then we have a reducing agent, which makes reduction happen. So a reducing agent makes it makes a substance lose electrons. Right, moving on, we got this example over there. Look at that diagram. Damn. Yeah, look at that diagram over there. We have we have atom A and atom B once again. As you can see, electrons are moving from atom A to atom B. So here's the explanation of everything that's happening over here. So A loses electrons, right? That means A is oxidized. Remember, oxidation is the loss of electrons. So A is oxidized. A gives electrons to B, reducing it. And what does that mean? A is the reducing agent because it causes B to be reduced. It causes B to gain electrons because A is losing electrons. It's giving those electrons to B, which causes B to be reduced, which causes B to gain electrons. Just make sure you understand me right here, people. Understand what I'm trying to say here. A loses electrons, right? A is oxidized. We know that because oxidation is a loss of electrons. So A gives electrons to B, reducing it. Reducing what? B, people. Reducing B. A is the reducing agent because it causes reduction. It makes reduction happen. It makes B gain electrons because it is giving B electrons over here. Okay, let's move on to the next one. So B gains electrons. Okay, B gains electrons. B is reduced. B takes electrons from A. Okay, it's receiving them electrons from A, oxidizing it. Oxidizing what? A. It's oxidizing A. It's causing A to lose those electrons because it's taking away A's electrons. Then B is the oxidizing. That makes B the oxidizing agent because it makes oxidation happen. It makes A lose electrons. People, come on, come on. So let's move on to calculating oxidation numbers. So I went ahead and brought you guys a little something something, hooking you up with something something that you're gonna need, that's gonna help you when calculating oxidation numbers, people. I have everything you need right here. Everything you need is right on this page, people. Just hear me out, listen, okay? So an element by itself is zero, like I showed you on the previous slide, which I might show here, right there. I'll show it right there, what I showed you on the previous slide, that NaCl, so oxidation numbers are zero because they're electrically neutral. Okay, so moving on, a monatomic ion, the oxidation of a monatomic ion is equal to its ion charge. For example, Na plus, Na plus, so oxidation number will be plus 1 because it has a charge of plus 1. It has an ion charge of plus 1. And then group 1A is always plus 1. So group 1A, that's just group 1. Group 1 being this one, it's always plus 1. The oxidation number is always plus 1. Group 2A, it's always plus 2. Remember that. You don't want to forget that. Okay, so group 2A is always plus 2. Then halogens. Halogens, which is this column here, this this group here, group 7A, group 7, they are usually, the oxidation numbers are usually minus 1, but they are positive with oxygen. So it's positive 1 if the halogens are paired with oxygen. Then we have H here, H, which is hydrogen. So it's plus 1 with non-metals and it's minus 1 with metals. So make sure you know on your periodic table which ones are metals, which ones are non-metals, because this here is very important. This here it can mess up everything. You can lose marks if you don't know this, because one mistake on the oxidation numbers, then everything is wrong. I want to explain everything later why I'm saying that if your oxidation number is wrong, then everything else is wrong. Okay, so moving on. O, which is oxygen, it's usually negative 2, but it's negative 1 in peroxide, which is H2O2. And then F is always minus 1. So whenever you see F, just know that it's minus 1. It's always minus 1. Its oxidation number doesn't change, just like the ones from group 1, the ones from group 2. Okay, now the sum of oxidation numbers for a neutral compound is equal to 0. Did you hear that? The sum of oxidation numbers for a neutral compound is equal to 0. So a compound on its own, it doesn't have an ion, it doesn't have ionic charge, so that means it's a neutral compound. If you don't see minus on top of a compound, -1, whatever, then just know that it's a neutral compound. Its oxidation number is equal to 0. Then sum of oxidation numbers for a polyatomic ion is equal to its ion charge. For example, SO4 2 minus. So its oxidation number is equal to -2. That's it. Then I have this periodic table here that can help you. Guys. This periodic table here, we have halogens over there. Those are our halogens. Okay, that's group 1, group 2, the ones that I explained over here. So every halogen here, every halogen is -1. Okay, just make sure you understand that one. Every halogen here, every halogen is -1, but they're positive when they're paired with oxygen. Remember that they're positive whenever they're paired with oxygen. So I got some couple of examples around here. I have some examples here. So number 1, we have MgO. So we're gonna find its oxidation number. So MgO, okay, first off, we know that O is usually -2, but let's see Mg. Mg is in group 2A, that's right, so it's always +2. So which one would you say we can start with here? The one that's always +2 or the one that's usually -2? Usually -2. The one that's always +2, right? So it gives us more, it's more accurate. Okay, it gives you the correct answer. This one is gonna lead you to the correct answer because it's always +2, it doesn't change. But this one, oxygen, is usually -2, -1 in peroxide. But then again, we don't have peroxide, so even that one is true. You can use it too. You can start with whichever, because both of them are don't change. This one only changes when it's in peroxide. So we don't have peroxide here, it's MgO. So here's what we can do. First of all, as you can see here, this is MgO. MgO doesn't have an ion, whatever. So it's the sum of its oxidation numbers is equal to 0. So that's what we know now. And then Mg is +2. O is -2. So can you see that +2 and -2 is equal to 0? So we're done. The oxidation number of Mg is +2. The oxidation number of O is -2. Moving on, number 2, CO. CO, well, we have to go back to our statements there and our periodic table. So C, is there anything about C here? Do you see any C there? C. No, I don't see no C. Then O, do you see any O here? Yes, we do have O. It's usually -2, but -1 in peroxide. Okay, so since it's -2, okay, then we have something. We have a starting point. We have oxygen being, its oxidation number being -2. And look at this, there is no ion here. There's no -1 or whatever, like in the next example. There's no -1 +1. So easily we can tell that the sum of oxidation numbers for this neutral compound is 0. So here we can say -2. So what's the number? A number that will sum up to 0. That will give you, that if you minus it by 2 will give you 0. It's obviously +2. There's no other number. So the oxidation number of C is +2. So that's what we're looking for. We're looking for the oxidation number for C. So oxidation number of C is +2. Okay, you don't have to do it this way, but I think this is a much quicker way and a more understandable way. Another way you can do it is, since there's C here, right, it's one C, you're gonna say X, and since we know that this is -2, we're just gonna say plus -2 is equal to 0, because this is a neutral compound and the sum of the oxidation numbers for a neutral compound add up to 0. Then X minus 2 is equal to 0, X is equal to 2, then you are done. Moving on to number 3, NO2 minus. NO2 minus, as you can see there we have it. We have a minus there, which means this whole polyatomic ion, this is a polyatomic ion, it has many atoms. A polyatomic ion has more than one atom. That's what it means. So this polyatomic ion has a a charge of -1, so its ion charge is equal to the oxidation numbers, the sum of the oxidation numbers for that polyatomic ion. So here we know that our oxidation numbers, the sum of our oxidation numbers will add up to -1. So we know that. Now we go back again on our periodic table and our statement. Is there anything about N? There's nothing about N. Is there anything about O? Yes, it's usually -2, but -1 in peroxide. Now, so that means we're looking for the oxidation number of N. We already have the oxidation number of oxygen, because we know that it's usually -2, but -1 in peroxide. So here we can say we have 2 here, so -2. We're gonna say -2, we times -2 by 2, because we have 2 oxygens, and that gives us, let me write it here, -2. Okay, -2 is the oxidation number for oxygen, but here we have 2 oxygens, so we're going to multiply that by 2, which gives us -4, right? So now we want a number. Okay, the oxidation number for N will be a number that if we minus it, it should give us -1, because it's the sum of the oxidation numbers for this polyatomic ion. So what's the number that will give you -1 if you subtract 4? Correct. So it's 3, guys. It's 3. 3 minus 4 is equal to -1. So the oxidation number for N is +3. Number 4, again we have another neutral compound. So it's the sum of the oxidation numbers add up to 0. So now let's see. We go back again to our periodic table and our statements. Does anything say anything about Zn? Do our statements say anything about Zn? No, I don't see that. Does our statement say anything about H? Yes, our statements do say something about H. Oh, my bad, guys. I forgot. There's an H here. Hydrogen. I forgot H here. Hydrogen. Yeah, so just add that H over there. So our periodic table says something about H, and our statement too. So H, right, is in group 1. Is in group 1, so it's always +1. So now we have the oxidation number +1. We don't have the oxidation of Zn, so that means we're looking for the oxidation number of Zn. And again, remember, we said H is +1 with non-metals and is -1 with metals. So zinc, is it a metal or a non-metal? Zinc is a metal, so zinc here will be -1. The oxidation number for zinc will be -1. But now we have 2. Oh, my bad. I mean, this zinc is a metal, so hydrogen will be -1, because it's -1. Our statement there says it's -1 with metals. So hydrogen here will be -1. The oxidation number for hydrogen will be -1. But now we have 2 hydrogens here. So -1 times 2, that's -1 times 2, that's -2. And then now we need the oxidation number for Zn is a number whereby if we -2, it must give us 0. And there's only one number that in the universe, okay, one number that it can be. That's +2. Or you can use the X method, where you say X, okay, X minus 2 is equal to 0, then you take 2 to the other side and you get the answer. Whichever suits you, whichever you're comfortable with, and use the method that you're comfortable with. Now we move on to number 5. Number 5 is BrO3. As you can see there's a minus there, -1, which means it's -1. The ionic charge is -1. So for this one, the sum of oxidation numbers is equal to, the sum of the oxidation numbers for this one is equal to -1. Right, now we go back again on our periodic table and our statements. So Br here, as you can see, it's a halogen, so there it is there. My apologies if it's not clear, but there it is there. That's Br right there. That's Br. So the statement for Br says it's usually -1, but it's positive with oxygen, because it's a halogen. All halogens are usually -1, but they're positive with oxygen. and look at this. It's paired up with oxygen, right? So Br is definitely gonna be a +1, all right? And then O is usually -2, but it's -1 in peroxide. So here, what we're looking for on number 5 is the oxidation number of Br, okay? So now, we don't know the oxidation number of Br because that's what we're looking for. So we start where? On oxygen. So oxygen is -2, okay? -2, since there are 3 here, we're gonna say times 3. -2 times 3, that's -6, right? So now we need the oxidation number for Br is a number whereby if -6, it must give us -1. So what number is that? 5. So the oxidation number of Br is 5. So Cl F3. F is always -1. And look at that, we don't have a minus or anything here. So the oxidation number, the sum of the oxidation numbers for this neutral compound is equal to 0. So now F on a statement that says it's always -1, okay? Then Cl is usually -1. But here the question was, I just wrote the examples like this, okay? I didn't write the statements. So the question here was find the oxidation number of Cl. So obviously we know that F is always -1. So -1, since there are 3 here, we're gonna times it by 3. -1 times 3, that's -3. And then what the oxidation number for Cl will be a number whereby if we -3, it must give us 0, which is +3, which is equal to 0. And you're done. That's it for this video. See you in the next one. Peace. Seriously though, please subscribe.